an application not only need GPU to execute its instruction, it also require some storage which can maintain data. Okay, a file system are the storage systems or used in the computer system to maintain persistent information for applications. Okay, a file is an abstract data type which contains a logical address space which contiguous. Okay, can be used to store persistent information. Okay, and a file system is a container for files. Okay, it means a file just an element of a file system. Okay, so a file system need to provide ways to organize, create, store, or retrieve, and even delete information from the file. Okay. From the application point of view, a file system or a file is an abstraction. So we assume there's a mechanism to maintain those persistent information or data for the applications. However, the actual data maintained by files in general are stored on devices, okay, and either block devices or network devices or whatever, okay. But in most of cases are block devices, like for example disk or flash memory. So most cases the file system use a block device underneath to define the data structure on the disk blocks. It also define how directory files and free space of the storage, okay, or disk, okay, to be maintained. Okay. Multiple individually managed file systems may be combined together into an actual view of a single hierarchical namespace or directory trees, okay, through mount mechanisms. Okay, that's the most modern operating system has this kind of mechanism or similar mechanisms. Okay, to put multiple file system together as a single hierarchical structure. Okay, and to support multiple file systems simultaneously or transparently from the applications. In general, there's a layer of abstraction between the physical file system and the application. Okay, and this layer usually we call it virtual file system. Okay, that are supported by most of the modern operating systems. Okay, operations needed or supported for files usually have the following types: create and open a file. Okay, and they may have create and open. Usually they use the similar interfaces. Okay, for example, in open file we give a file name. Okay, then the system will search the directory structure on disk for a special entry associated with this file name fi. Okay, and during the process of open a file, operating system will move the content of this associated attributes of this file fi to memory for subsequent efficient access. Okay, and these attributes usually include file pointers point to the last read-write operations. Okay, but maybe in the process fashion. Okay, so each process open the file has a associated file pointer. Okay, and access write. Okay, maintain what kind of operation which are granted for this opening. Okay, and file open account usually used to record how many processes are currently accessing the same file. Okay, open the same file simultaneously. Okay, and that's part disk location information usually contain those disk addresses of this associated file. Okay, and for write or read operations. Okay, reposition. Okay, operations. It means it move the file pointer around. Okay, delete and truncate. Okay, delete means you remove the content from the file system of the file. Truncate means discard the portion of the file contents. Okay, and corresponding to the open or create, there's a close file operation used to store back those in-memory file attributes. Okay, where after open, for example, the file pointer or access write or the information of these attributes stored in memory, and during the close operation, those information may be or attribute may be updated, so they need to write back to the disk if necessary. Okay, and if a system support multiple process can open the same file simultaneously, then the close may just decrement the file open account. Okay, until the last open was closed. Okay, then those modified information may need to be written back to the disk. Okay, to access a file, in general, there's two kind of accessing mechanism. One is sequential access, another one is direct access. Okay, or sometimes we call it random access. Sequential access means you access the file block by block, and these blocks are in logical continuous way. Okay, so that means you do next block. Okay, instead of doing specific number of specific block. Okay, so the operation will be do next, right next, and rewind. Rewind means we reposition the file pointer to the beginning. Okay, so as the figure shows, okay, the file can be treated as a contiguous logical space. Okay, starting from the block 1 to block n, for example, or block 0 to block n. Okay, so the current position may be in the middle, and do next or right next, they will read the next content. Okay, it is fine, but rewind will move the current pointer or file pointer back to the beginning. Okay, for direct access, the interface will be read. N is the position of the read. Okay, or block number. Write n is the number, the block number. Okay, for to be right. Okay, position to n. Okay, that means you move the position to a particular way, position, the location. Okay, so a sequential access can be simulated by direct access operation. For example, rewind means you change the position to 0. Okay, position to 0. And if we do next, that means we do current position, and then position to the next one. Okay, okay. The right next means you write the current position, and then position to the next one. Okay, so these are, if a system support sequential direct access, then the sequential access can be emulated by the direct access. However, if a system support sequential access, then other mechanism to make it look like or to emulate the direct access interface, then the implementation may be a little bit difficult. For example, to simulate re-earn in direct access by sequential access, then we need to be able to move the position, current position, to position n. Okay, that is not a there's no easy way. Okay, the most intuitive way is that first we rewind to the beginning and then do it n blocks, and the last read and do a loop to do it n times, and the last read will be the re-access required. The previous n-1 read, you just, the purpose for that is just skip these logical block numbers. Okay, so to implement sequential access by direct access is easy. Okay, but to implement direct access by sequential access, it's not very efficient. Okay, you cannot find an efficient way to implement. Okay, a physical disk in general can be divided into partitions. Okay, the purpose for the partition is because most quantum file systems, okay, they associate with partition. So partition related to logical entity of file system, but disk is the physical devices. Okay, and disk or partition may be array protected against failure. Okay, array is a redundant array of inexpensive or disk. Okay, the term abbreviation of these terms. Okay, that means you put a lot of disk together and management put them together to integrate them together and to gain some reliability or performance gain, or even the fault tolerance gain. Okay, and disk or partition may be used in two different modes. Okay, the first one is low mode without a file system, just a physical disk. Okay, you use the underlying device driver or disk driver to access the disk directly. Okay, instead of go through the operation the file system. And that's all right. Okay, and the second one is formatted with a file system. That means because different file systems may use different way to management these disk blocks. Okay, so formatted means you make this disk become manageable by a particular file system. Okay, so partition sometimes we know as a slice or mini disk or vault. Okay, an entity which contain a file system, usually known as a volume. Okay, and each volume contain a file system. record file systems information in the disk device directory, okay, or volume table content, okay. So here the directory is a physical device directory, not the file system directory here, okay. So the term of the directory, if we associate with the disk or device itself, is a device directory. If the directory, the term associated with a file system, that means it's a file system hierarchy. Okay, they have different meanings in this different terms, okay, in different environment. Okay, so sometimes we call it volume table of contents. Okay. So here, a device directory means each physical device will have this directory. Okay, the reason is that before this device can be management, okay, we create this directory, okay, and the number of entries represent how many files can be associated or created management by this particular device. Okay. For example, in this particular example, if this device we would like to use this device to maintain N files, okay, then we need to have a device directory contain N entries, and each entry eventually can be used to store information about a particular files, okay, and specifically they will store the address information of a particular file. Okay, so this device, if this device will be used to manipulate N files, then we need to have N device entries in this device directory, and each entry eventually can be used to maintain a physical file, the information about a physical file. Okay, and then the underlying physical files, every physical files may occupy some a number of blocks. Okay, and this information will be stored in a particular device directory entries. Okay, so a device directory is a collection of entry containing information or file attribute about all files will be stored in the particular device. Okay. A typical file system may be organized in this way. Okay, for example, a physical disk one may contain two partitions, and each partition have its own directory, a device directory, okay, and associated with those files. Okay, so for example, partition A, the directory of partition A may contain N files. So the directory path will have N entries, and the partition B may be used to store M files, at most M files. Then the directory path of this partition B will have M entries. Okay, and also in the right hand side, this particular partition C may be organized by a concatenation of two physical disks, for example, disk 2 and disk 3. Their storage combined together, be used for this partition C. Okay, and then the directory, for example, the partition C may be used to maintain a huge number of file entries. Okay, for example, H, number of entries will be H. Then the directory path will have H entries because the H is a huge number. So maybe the files associated can be maintained by this partition C, and the physical space will be larger than physical directories, devices, or disks. So you can put two disks together as a logical partition. Okay, so depends on the way we try to organize the file systems. Okay, well, some file system, the total number of files may be smaller, so you can physically make a physical disk to be multiple partitions. Or if a file system, the purpose of a file system will be to maintain a huge number of files, then we may need to put several physical disks together as a single partition. Okay. The mounting of file system in general has this can be used to put several file systems together as a single tree. Okay, so we can mount a file system to existing tree. Okay, for example, in the left-hand side figure, A is the existing file system. Originally, this file system has this physical, this hierarchy. And there's a B, an unmounted partition. Okay, itself is a file system. Okay, but it's, and then if we mount this unmounted partition to the existing file system and mount it in the place of /users in this subdirectory, then after the mount, the new file system will be like the right hand side. You can see that the logical, the tree, original tree on subtree on the users was replaced by the mounted part partition. Okay, and the original subtree become invisible. Okay, after this mount. So if after mount we still like to have the original subtree users can still be visible, then you cannot mount this unmounted part into users. You need to create a new entries under the stage. For example, stage, you create a new entry under this root directory, maybe called users1. Okay, then you mount this unmounted part into the users1. Then the after mount, the file system will contain two subdirectory /users and /users1. And /users will be the original subtree of users, and /users1 will be the new mounted part. Okay, so it depends on how you merge this unmounted part into the existing file system. Okay, the result can be that will be different. Okay. Okay. Most modern file system support the directory structure. Okay, and directory is a special file in the file system. Again, it is used to maintain the partition information, but this partition, the special file, the purpose for this special file is maintain the information about a group or collection of files. They have some logical meaning to put them together in a directory. Okay, so the operation of the directory, this special file directory, may be a little bit different to a normal file. Okay, for example, if a file is a directory, then we need to have a way to search from this directory, especially search a particular file by given attribute of the file, for example, the name or part of the name or whatever. Okay, and from okay, and create delete a file entry from a directory. Okay, list all files from a directory. Okay, and rename the file, give troubles the directory hierarchy. Okay, so even it's a directory may contain subdirectory and so on. So under a directory, the troubles a directory may extend or can be used to navigate all the files under a directory. Okay, the advantage by using this directory structure in a file system is become efficient to locate a file quickly, because if without a directory, then all the file must be flattened under the name of the file. It may become very long, because to distinguish a file from the other, we need to have different names. Okay, so with the directory, then two files may have the same name as long as they are in different directory. Okay, so you can have a data file for different projects. They all call data, but these data files are in different, and each project has its own directory. Then as long as the directory name are different, then the file under a particular project will be also their name may be the same, but they have different meaning and so on. Okay, so naming become much easy. You create a name for users, because two users or two projects may have used similar or same naming structures. Okay, but in different place. Okay, they are represent different files. Okay, because they are under different projects, for example. Okay, and also become possible. Okay, a physical file may be associated to multiple directories. Then this file can have multiple names. Okay, but they all they all related to the same physical files. That become possible. Okay, and the other way, the last advantage is that we can logically group files by their properties or their characteristic together. Okay, so for example, you have again Java programs, they put them together under directory called Java or Java programs, and you have some video games. Okay, they can do, or under the video games subdirectory and so on. So it becomes much easy to trace or to find out corresponding files from huge file systems. Okay, the type of the directory in the file system. In general, we may have a single label directory. That means a single directory for all files. Okay, in the early PC MS DOS, they use this structure, and also maybe, for example, in the left side figures. Okay, the directory contain all the file. Okay, so this single label directory is very similar to a device directory. Okay, because in device all the files has an entry in the device directory. But here this is a similar way. Okay, this file system only has a single directory, so all physical files must have has an entry associated to an entry in this directory. Okay, and because it's become difficult to name, because all users may have a similar name, same name, then you need to extend, create a name. For example, the user Jack create a name, a Java program called Java, but because the other user Mary also has a Java project, she also like to name it its program as Java. Then we need to distinguish the two files. For example, the Jack's Java will be Jack Java.c, Mary Java.c. Then the file name will be something like this. Okay, it's very difficult to remember and distinguish it. Okay, so two-level directory means we give each user its own directory. Okay, that's most of the early time sharing system or early multi-programming systems. Okay, they use this mechanism. Okay, so we have a master file directory. Every user has a entry there, and then under each user it has a user file directory. Okay, contain all the files belong to that particular users. Okay, so for example, here you can see in this two-level directory, the user 1 and user 3, they all have this file A and tester, but they are in different scenes. Okay, user 1's A and user 3's A are different. Okay. So every user become much easier to name, maintain, or manage its own files. Okay, but again, only solves part of problems, because every user may have multiple projects, and every project may use the similar name. For example, test data, they would like to name it as a test, but because you have multiple projects, so it would be nice to be able to create subdirectory on demand. Okay, and not all the files belong to the same directory. User must be in the same directory. So we have 3 structured directory. So you can create subdirectory by user dynamically. Okay, and later, if a file need to be shared, physical file may be shared by different projects. Okay, then it would be nice to be able to create, we call it a cyclic graph directory. Okay, so subdirectory file can be shared, okay, by different subdirectory. And the last one is a journal graph directory, most general and difficult to manage. This we will discuss these 3 in the following slides. Okay. The 3 structured file directory will be something like this. For example, we have a root directory, and under this root, you may have different subdirectory. For example, spell is a directory. And inside the spell, we have a mail directory, and then program directory, and then object directory, and so on. Okay, so for this, we can dynamically allow user to create subdirectory on demand. Okay, so we get the advantage of all the directory. Will be efficient search. Okay, we follow this directory structure. Okay, because the reason created have some semantic or logical meaning, purpose, and you can group in related file together. Okay, and for this 3 structured directory, usually we have a 2 way to locate a name. The first one is actually path name or relative path name. Okay, the actually path name is that this name we name the file starting from the root directory. Okay, for example, here we have /spell/mail/pro/object there. Okay, they will always starting from the root directory. Then okay, like this rectangle. Okay, will be the the path, okay, starting from the root. Okay, and another one is relative path name. Okay, that means instead of specify a file, always starting from the root directory, we create an environment parameter, okay, or environment variable. Okay, in the file system. So you maintain a current directory or working directory information. For example, this C change directory. The working directory now is in spare mail program. So this this directory become working directory. Then we can just reference this object by this spare mail program object by using this relative path name without obj. That will be a relative path name relative to the current working directory. You can see that if a path name started with root, they always has a leading stage. Okay, if a path name, this convention is in Unix or Unix-like. Okay, in Windows they use the backslash. Okay, not the slash. Okay, but with the similar meaning. Okay, path name started with a slash or special symbols. Means an abstract path name, but path names started without any just a simple name. Usually means it is a relative path name relative to the current directory or working directory. Okay, so both ways you can specify to the same file. Okay, a cyclic graph directory will be something like this, like the right hand side here figures. Okay, here we can see that we have two file which contain two direct entry. One is in /dic count. Okay, and another one is /spell count. They all point to the refer to the same file. Okay, so a file may have different names. Okay, if we delete a file, we can /dic /w /list. Okay, then the file /dic /o may be lost. Okay, because the list is removed. Okay, they point to the same file. Okay, without proper management. Okay, so and possible way is that we maintain a reference count, record number of names. Okay, that is sometimes we call this hard links. Okay, so the file associated with /direct O and /direct W /list. Okay, there's a reference count number 2 associated with these two files. So when we delete /dic/o, the count will be decrement by 1. Okay, and so on. Okay, and the second way is that we use a new directory entry type. Sometimes we call it sublink. That means it's a name or pointer to an existing file. Okay, so instead of directory associated to the existing file, but we give the original name. We may store original name in the file. Okay, so that's we call it soft links. Okay, so the semantic of the soft link is a little bit different. Okay, although they semantically they all point to the same file, but by using different way. Okay, the first file, the original file original name, physically use a hard link physically point refer to the file, but the soft link, they are not directly associated to the file, but instead maintain a pointer to the file. Okay. And so to resolve the link, the soft link, we need to follow the pointer to locate the file. Okay. So when delete this DICW list, okay, if only the reference count is decreased by one. If reference count becomes 0, then the file can physically be removed. Okay. So for the soft link part, we will discuss that later. Okay. Also, the general graph directory. Okay, we will see that the purpose of the soft link. Okay, it's here. The cyclic graph directory means you will not this. The file may have multiple names, but this graph hierarchy is acyclic, so we cannot allow a cycle to exist. Okay, but in the general graph directory, the cycle become possible. Okay, and if we allow cycle, then the reference count mechanism, okay, used in this maintain multiple names will become useless. For example, okay, in this particular application examples, okay, when we create this /AVI/book, okay, as a pointer point to this /gin/book. Okay, they would like to point to associate to the same directory. Okay, the directory B. Okay, then the reference count of B will become 2. If the first one, first creator is the /gin/book. Okay, then so once, and then we create /gin/book/AVI to be /AVI book. Okay. Then the count of /AVI/book will become 2. Okay, now we have a cycle. Okay, is it in /AVI book to /AVI book AVI to book? Okay, so we have a cycle here. After delete gin book, if we delete gin book, that means the reference count of B will become 1. Okay, and delete AVI book. So count B is 0. Okay, but count AVI book is 1. So we have a situation that the AVI book is already gone because the directory B, the count of B is 0. So the physical directory of B will be removed. So the AVI book become floating, point to nothing. Okay. So general graph, if cycle is allowed, then it become, we cannot use a simple way to the Lorentz count mechanism become invalid. Okay, so the solution is that we avoid general cycle. Okay, hard link to fires, but not subdirectly. Okay, here we can find out if hard link, the hard link point to directory, then directory may point back to its parents. So if we always refer only the file allow multiple names, but directory did not allow multiple names, then we are okay. Okay, or maybe we need to do some garbage collection. Okay, beta garbage. Another way is we before adding a new link, we always check cycle existence. Okay, if a cycle exists, then we cannot allow this new name be generated. Okay, and the last is use sublink instead of hard link. Okay, so we did not actually create a reference to the file instead. So by using sublink, we did not increase the reference count. Okay, so every file can only have a real name, but a sublink just a pointer. Okay, instead of name. So a file only have, okay, so always use sublink. Okay, without use any hard link. Okay, so. And here the sublink means we did not we create, for example, a book. /book / AB guy /book. Now as a gene book. Okay, then instead of increment the reference count of B, we create a real entry, a real file of /ABI/book. But within this file, we store the real name /gene/book, okay, instead of create a reference to this directory. Okay, but we maintain the page name, store the page name into the file of this book. Okay, so there's a special file we call it sublink. Okay, and whenever we open a file which is this sublink type, then we know that the content of this file is the page name of another file. Okay, so then we don't increment the reference count, and so instead of, okay, so there's no physical cycle will be created, although they may have a virtual cycle. Okay, goes through this sublink, but sublink, when we try to open the file and the file is a sublink, and you try to follow this sublink to the file, to the physical file, to the real file, but the real file is not existent, then the sublink become invalid. That's it. Okay, we're not do any harm for the system. Okay. The problem is that the file just been deleted. Okay, it's not exist at all. Okay. To implement a file system, in general, we maintain a file system and all this logical structure associated with the file system in physical disk. Okay. And this file system give the application an efficient and easy way to be able to store data, okay, and locate and retrieve data, okay. And to managing the file in a disk much efficient. In general, every file will have a file control block associated with, and the content of the file, this file control block always usually maintains some metadata about a file. For example, in the right-hand side, permission, okay, of the file, who will be allowed here to do what kind of operation, and file some timing information, creation, access, last update, and so on. Okay, and the owner of the files, like the group of files, and the access control list of the files, and so on. Okay, and the current size, okay, of the file. Okay, and also last part is the file data blocks or pointer to the file data blocks. Okay, the actual location of the content real data stored. So usually is direct disk addresses, okay, or block addresses of the disk. Okay, and the disk with, if a disk is formatted with a file system, usually we have a boot control block to contain information needed by a system to boot operation system from that particular volume. Okay, and each volume usually has a volume control block to contain detail of that volume. Okay, so directories are used to organize file and store their file control blocks. Okay. So this is file system directory, not a device directory. Okay. So if a disk contain file system, then in that disk we would have a boot control block contain information about how to boot operation from that particular volume. Okay, and the volume will have volume control block contain information about the volume. Okay. When operating system booted and try to launch file system, okay, associated to the disk. Okay, then first thing is that some file system attributes may need to be cached into the memory. So the subsequent access to that particular file system will become much efficient. Okay, and this initialization will create an in-memory file system structures. Okay, out of this disk file system structures. Okay, so that's the purpose here. So when the operating system launch is associate or initialize the file system, then first thing is that you retrieve this directory information and file control blocks into memory, okay, associated to a particular file system. Okay, in general, it's something like this. Okay, so we have a kernel in memory. We maintain directory structure about the file associated file system. Okay, and then inside this directory structure, each entry will also map to a directory entry in the file system.